This is the presentation of my mini project, VPN Lab, the container version. And my name is Liu Kai, and my trade number is GS613019. This one is the task 1. It's about network setup. For the testing, there have 4 objectives. One is the host you can communicate with VPN server. VPN server can communicate with host V. Host you should not be able to communicate with host V. And it run TCP dump on the router and sniff the traffic on each of the network. And this is the lab environment setup figure. First, start the Docker and use the new terminal, and we can use in the host U to ping the VPN server. In this future, you can see that host U can communicate with the VPN server, and then use the VPN server to communicate with the host V like this. In the future, you can see it ping it successfully. And then you can see here that host 2 cannot communicate with host V. For the packets, it's 100% lost. And then listening at the ETH0, and you can see the ICMP and ARP message were heard, during which time the client sent pings to both the server and the internet device, but only the server responds to it. And next, listen to the ETH1. The first ping the wrong object to this IP address, and the results only saw the ARP message, and then ping this IP address. So you can find the ICMP message. Then is the task 2 is create and configure TUN interface, and we need to name the interface, set up the TUN interface, and read from the TUN interface and write to the TUN interface. Here is the TUN interface Python program. You can see run the program directly on host U can be seen in the future. The TUN0 interface is found. To modify the interface name, only need to modify the procedure in the following future and modify. You can see you can change it to for my last name is the Liu, L-U. And you can see here and the TUN program the following this statement. You can see here the LIU, the interface name is changed, and then the TUN interface will be read in this assignment. IP packets were what exists the TUN interface. Each IP packet flags can be written out individually by converting the data received from the interface into Skype IP project. Instead of using the while loop found in TUN, TUN.py, use the one below, and on the host U, ping a host in this IP address network. You can see that. So it's worth nothing when ping this IP address. Our pipe interface does not receive a message on the interface, but the endpoint that sent the ping request receives a message. Guess because the system found that it was sent to its own address, so it was replaced with a loopback address. I use TCP dump to listen to the loopback address, and that's exactly what happened. And number 2 is sending a ping request to any address under this IP address. It's unresponsive on our terminal interface, so no data is sent or received from the interface. and they're using the following code to write a message to simulate the receipt of a message, since any message whose IP starts and ends on the local machine will be received by the kernel, and messages that do not meet the segment's requirements will be rejected. The message sent and received here are only used to show that the code can generate the corresponding message, write a message, and generate the corresponding message. And task 3 is send the IP packet to VPN server through a tunnel. So putting a complete IP message into a TCP or UDP message and sending it to the target is sending a message through a pipe. We are using UDP for this time task. So for the server program, you can see in here always listen to pop 9090 and outputs to display all incoming message and disassemble the message to display the internal messages, and then modify the client program, replace the client part of the code as follows. So if you run the above programs separately and ping this IP address on the client side, you will receive the following information on the server, and the client will automatically transfer this IP address to the LU0 interface we said before, but it's not a real interface and cannot really send a message, but our program reads it and sends it to the server we set up as a packet. The server unpacks and reads the message we sent was actually sent from the 53.00.99 to 53.2. The task 4 is set up the VPN server. First create a TU interface and configure it, and get the data from the socket interface and treat the received data as an IP packet, and then write the packet to the TUN interface. So modify the received TUN point py with the previous where code to a new server program. You can see as shown in future, the output shows that the code correctly run to send the SMP message transmitted in the kernel. So it's clearly through the Wireshark that host VPN has made its response as shown in the future, but apparently the client did not receive it, which will be refined in the next task. And task 5 is handling traffic in both directions. You can see the client and server code is the same, only the IP address sent is different. Even the listening port is the same, because in fact this part of the client is responsible for the work that the server should be responsible for. That part of the client's code show is responsible for receiving and forwarding the key part. And you can see host U can ping to host V normally, and then using the Wireshark to capture the packets of host U ping host V, you can see the results as shown in here. And task 6 is the tunnel breaking experiment. While keeping the remote login online, breaking the tunneling servers of either the client or the server, the same situation occurs. Like no task can be entered in the remote login screen, and no new output will be produced anymore when reconnected to the service for a short time. The black logged message in the TUN file is released one by one. And task 7 is the routing experiments on host V. The operation steps are shown in the future. First, check the IP route on host V, then delete the default and edit. And finally, I ping host V on host U and found that I could still ping through. You can see here there is 0% packet loss. And task 8 is the VPN between the prevent networks, and the network topology for this section is shown in the future. It's required to interpret and prove both ends by erecting a tunnel. So it can be noticed by looking at the Docker configuration file that to only adds two slave machines to one for the so-called clients. The container is run by the following command. Look at this. So first of all, we'll verify that it's not interoperable and only show here that the left side cannot be pinged to the right side. You can see here the 100% packet loss, and then open the program on the client and server at the same time. At this point, to the left side is ready to communicate with the right side. You can see here is the 0% package lost, so it can ping through. And task 9 is the experiment with the TAP interface. Our previous experiments were based on TUN technology, which is very similar to TUN, and so that its code is also very similar. TUN's interface is built at the layer 3 network layer, while TAP is built at the layer 2 MAC layer. So therefore, the message on the TAP should include the MAC header. We can still experiment with the same container as before. The only modification is that we set the interface to TAP when we set it up, as shown in the future. Here we change the TAP. So next, to write the TAP.py with only modification to the previous TUN program. You can see here. And then the next test was conduct, and the results as shown in the future. You can see from the results that the forget message was received. You can see here. So that's all the task for the mini project. Thank you for listening.